So what exactly makes a model non-linear? Let's start by thinking about what makes a model linear. Here's the equation of a line. So our dependent value y is equal to an intercept value, that's where the line crosses the y-axis, plus a slope multiplied by our x value. Beta naught and beta 1 are regression constants that we're going to estimate. So they're unknown, but they're constant. If we take the derivative of this thing, we get an expression for the change in y for a given change in x. And if we work through the calculus here, we end up with beta 1, which is simply a constant. We don't know what that constant is, but it doesn't change. As x changes, the rate of change in y is a constant. This is true even for more complex multiple regression equations. Now we have multiple values, x1, x2, and possibly more. In this case, we have to take the partial derivative of this function because it has more than one variable. So the partial derivative of y with respect to, say, x2 ends up being simply a constant, beta 2, plus all these other things, which are, again, in general changing, but when we're calculating the partial derivative, we're holding all of these things constant. This is the rate of change in y for a given change in x2, holding everything else constant. And again, we end up with something that does not change as a function of x2. x2 doesn't appear anywhere here on the right-hand side. So that's what makes this thing linear. The rate of change with respect to a given variable x is a constant. Let's think about a different equation. Here we have the species richness curve, so area sampled, in this case it's in square meters, and as we go up we get increasing numbers of species in our sample, and it typically has this kind of shape. It's known as a power curve, and our value, so the equation for this line is S is equal to a constant c times a raised to the power z. If z was 1, this would again fall back to being a linear equation, but in general for power equations z is not a constant but an unknown, so it can actually take on any value. If we take the derivative of s with respect to a, so now we have the rate of change in s for a given change in a, we end up with this equation, z times c times a raised to the power z minus 1. Unlike before, this thing is now no longer a constant with respect to a. As a changes, so does the rate of change in s. That's what makes this equation nonlinear. The rate of change in s with respect to a depends on a and is not a constant. As an aside, if we take the logarithm of both sides of this equation, so now we have log of s is equal to the logarithm of c plus z times the logarithm of a, this equation is now linear again. Taking the derivative, d log of s with respect to log of a is equal to the unknown constant z. There's no log of a on the right-hand side anymore. So for this simple nonlinear function, we have a relatively easy way to make it linear, and that improves the way that we can estimate these constants. But for many other kinds of functions, we don't have the luxury of a simple transformation that will linearize the equation, and we have to use special methods in order to estimate the constants like c and z in our models.